In this video, I'll cover the crystal field theory. Here I have an electron configuration for cobalt. So cobalt has argon brackets, abbreviated form 4s2, 3d7. And then I have the orbital diagram form where I drew in the boxes with corresponding electrons. If you're a little confused on how to draw the electron configuration and the orbital diagram, please refer to those particular video in the beginning of Unit 9. All right, so I want to label which one is electron configuration and which one is orbital diagram. So this one is the electron configuration. And this one is the abbreviated version, and this is the orbital diagram. And the orbital diagram is also the abbreviated, it's a shortened version of cobalt. Now, if you look at the d orbital in particular and the s orbital in particular, they look like they're in that same level. But if I were to kind of like zoom this out and look at all of the levels of each orbital diagram, it actually are in different energy level. So you see where on the left hand side, you see the increasing energy, 1s, 2s, 2p. So where I'm looking at right here, that 4s and the 3d is actually right here. Here's my 4s, and the 3d is after the 4s because it's a little higher in energy level. And even all these little lines, what do those lines represent? Well, those lines represent individual different types of orbital shape, and I'll show you those shape in a moment. But what I want you to see is that all of these 5 orbitals are degenerate, meaning that they are all at the same energy level. This one, this one, this one, this one, this one, all representing the shape of these guys. They're on the same energy level. They're not different. 3D is definitely different from the 4S and the 3P and 6P, right? But individual shape, the shapes in here, they're all at the same energy level, meaning that the electrons that carry within these shapes carry that much energy level. Now, this is just cobalt when it's by itself, when it's a free energy form. Free element. But when it starts to bind and forming a ligand, forming a complex ion, coordination compound, then things get a little more tricky. So, in complex ions, the metals are no longer degenerate, meaning that they are no longer in that one straight line. This is where the crystal field theory comes in, that they are no longer degenerate when they bind to a ligand. So then what do they look like? Well, they look sort of like this. The degeneracy is no longer there, but rather split into 2 forms, where the Z to the square, x to the square, and y to the square looks like is on the higher level. Where are those? Those are these shapes, okay? These shapes. And then the one on the lower energy level are here. Now, why is it so like that? Well, it's sort of outside of the scope of the class, but we can discuss it more in office hours. All right. Now, because they have split, this is called the crystal field splitting. There is a difference in energy level from the top and the bottom. Okay, you see how there is a difference in the two, and that is represented by the delta. The delta, the magnitude of that splitting really depends on the ligand. Here it's ammonia, but if it changes to, say, water, then that will either increase or depends on what ligand it's attached to. In fact, let me show you all the potential ligands there are and if they're going to even split higher or lower. So if in this scene right here, this is, by the way, not in your reference sheet, so probably good idea to have it. If it's attached to something like ammonium, which it is right now, it's going to split fairly quite high. But if it's going to attach to all of them are bromine, then that means the difference in this delta is going to be that change. It will be the crystal field splitting will be very low. So I have drawn this dotted line here. That's sort of like the cutoff point, okay? Cutoff point where in which on the left-hand side, we consider that having this small splitting. We consider that having the weak field ligand. Okay, we call it the weak field ligand, or you might hear the word high spin complex. Whereas on the right hand side, we consider that having a large delta, the large crystal field splitting, and we also denote them as a strong field ligand or low split spin complex. I know, kind of sounds all confusing, but they all kind of fall in that same category. So let's look at some examples. Okay, so here, this one is NH3, right? So NH3, so you see how the split is very big. If the split is big, how can we arrange now what we used to have was the electron configuration or orbital diagram. How can we arrange these electrons? Well, recall what the cobalt electron configuration and orbital diagram used to look like. So cobalt, when it's this one happens to be cobalt 3 plus. Okay, so cobalt 3 plus has bracket argon, and then it would have of 3d. My periodic table is over there, so I keep looking over there. 1, 2, 6, 3d6. Okay, and again, if you want to know how I did this, you could go back and look at the electron configuration video. But essentially, basically what I did is cobalt in neutrality is argon and 4s2 and 3d7, I believe. Yes, 7. So I need to knock down 3 since it's plus 3. So I get 2 from here and 1 from here. So hence why 3d6. Okay, so I have 3d6. That means there's 6 electrons. So when it's a free atom, or this one is free ion, we have 6 electrons. 1, 2, 3, 4, 5. So we've split them up all into ones, and then now we need to pair them up. So 1. So with this, we did this for the energy diagram for orbital diagram for cobalt. And then, but when it splits like this, now is it going to, which one's going to go where, right? First, what we're going to do is we're going to fill up the lowest energy first. Okay, so we're going to fill up all 6 of them, try to fit them all of them. So 1, 2, 3, so no more room, 4, 5, 6. So all of them fit in the lowest one and nothing will be on the high. So you can see how this is considered to be a low spin complex, meaning they're all on the low side. The electrons are all on the lower end. If they have this strong or large difference of the crystal splitting. And then we have a next portion. So this one was for NH3, so it's on the right side. So let's look at something that's on the left side of the dotted line. So that one was with no ligand. This is with the ligand. And let's look at the one with no ligand first. So we knew that there was 6. 1, 2, 3, 4, 5, 6, right? And then with the ligand, this one is water now. So I have water attached, so it's on this side. Well, if it's water and then it's low spin, it's going to fill up as spread apart as much as possible first, and then it'll go into the lowest energy level to pair up. Meaning first it's going to split up all of the 6 electrons like this, because they're in a low, so electron could reach the little higher ones too. They rather do that. It's more favorable to be unpaired. And then the 6th one has to go somewhere, and so it's going to go occupy the low one. And this one is considered to be a high spin complex because it's able to reach the higher level ones. But overall, it's called weak field ligand, or it's small delta because of the small delta or crystal field splitting. Now let's do a learning check. We're going to do one at a time to kind of see the whole picture together by utilizing different ligands this time. Here it says write abbreviated electron configuration of cobalt 3 plus, then draw the orbital energy diagram. So try this one and come back. We've already covered it before, but I want you to try it and come back. On the left-hand side is the electron configuration, and the right side is the orbital energy diagram. Now, if this cobalt is bound to this 6 of iodine, okay, or I should have a negative there, and forms a complex ion of cobalt I6, 3 negative. Draw the orbital energy diagram for the d orbital. Okay, draw the orbital energy. Oh, I should. This is weird. Draw the new d orbital energy diagram. So this should be gone. Okay. All right. So let's go ahead and try the first one, and then you try the second one. So the new one, we know that it's going to split off. So we have 5 lines here. We know it's going to split off, where in which 2 is going to be on top and 3 level is going to be on the bottom. But we need to kind of go back to that chart where it determines, well, is it going to be a big splitting or a large split, or is it low crystal field splitting? So I have that in the previous slide. And so we have iodine. This is a small crystal splitting. So if it's a small crystal splitting, this is considered to be right here, very small. So I'm going to write small. So if I were to, I'm going to transfer all the electrons. This is without, this is cobalt 3 plus before it bonded to any ligand. Now it bonded to the ligand, and because it's small, it's going to occupy all the electrons, going to occupy every orbital as possible. Then it will start pair up if it has to. Try the next one and then come back. And here is the key.